Welcome back. You recall in the last lecture I described that there are three ways to treat cancer: surgery, radiation, and chemotherapy or drugs. In the last lecture I talked about surgery, and I showed that you can cure cancer if it's localized, you can reduce the tumor burden. If it's spread, you can diagnose using surgery. Now I'd like to move to radiation. Radiation can also cure cancer if the cancer is localized. But more typically, it's used along with other methods of treatment. This is called adjuvant therapy. Adjuvant therapy, using along with other forms of treatment. I want to introduce this treatment with a story of a man I'll call James. James went to his optometrist for a checkup. And the optometrist took a careful history of his vision. James mentioned that sometimes he saw light flashes when he was reading. So the optometrist dilated his eyes using eye drops and dilated his pupils and looked into the eye, and he saw a ominous-looking growth at the back of the eye. Later that day, James went to an ophthalmologist, that is a physician trained in diseases of the eye, and got a diagnosis that was quite a scary one. He had a choroidal melanoma. This is a photograph of an eye in a patient with a choroidal melanoma, but here's a diagram of a cross-section of the eye that shows you what we're talking about. Here's the lens of the eye, the cornea, and the lens of the eye is here, and the light goes in and it goes to the back of the eye, the retina. And behind the retina is a layer called the choroid layer. And in the choroid there are some pigmented cells, and James had a tumor of the pigmented cells of this layer. It's rich in blood vessels behind the retina. It's a pretty rare tumor, a choroidal melanoma. There's about 2,000 cases a year in the United States. But it's a serious tumor. Choroidal melanomas can metastasize and kill people. They're treatable and they're curable if they're localized. And James seemed to have one that was localized at this time. Now, the treatment is surgery, obviously, and the surgery can be of two types. It can be radical surgery where you remove the whole eye. That's called enucleation of the eye. Or you can treat with radiation. James wanted this eyesight preserved as much as possible. He wanted both eyes to be functional. And he chose radiation therapy instead of surgery. And he didn't choose typical radiation therapy, but a new type called proton therapy. To review, radiation comes from atoms that are unstable, and they release energy in the form of photons, and they're called, and they also release particles as well. When the energy of a radioactive element is incoming to a person, it interacts with the tissue, and some of that energy is absorbed by the tissue. And so the energy coming out of the person will be less in amount. It's the same thing with light energy. Light energy is now hitting me, and it's all being absorbed by me. You don't see any light coming out the back of me. And in this case, the radiation comes in, and a lot of it's going to be absorbed. If the environment is living tissue, as this cartoon indicates, if it's a person, as the radiation passes through, it's going to damage tissue. It's going to damage normal tissue, and will also damage cancer tissue. Typical radiation used in cancer treatment releases X-rays. The problem of collateral damage is a real one, because the X-rays are passing through the tissue and they're doing damage as they go. For the eye, this is especially acute because the eye then can be damaged in this delicate nerve cells in the retina, and the radiation is going to have to pass through the retina to get to the choroidal tumor. So this could be a very dangerous situation if its standard radiation is used. In James's case, he was treated instead with protons, not photon beams, not beams of energy, but protons, highly energetic particles, positively charged particles that are released from atoms. And in the case of protons, they deposit all of the energy at the tumor site. In other words, they go through at a low energy, then they reach the tumor site and they release all the energy if you focus them in the right way. So this is a diagram of, on the y-axis here is the relative amount, the dose in energy, and this is the penetration depth in tissue in centimeters. And for X-rays, as the X-rays enter the tissue, they get absorbed and the energy is released. And you see that as you go through the tissue, energy is being released everywhere. And there's going to be a lot of damage there, including, for example, if this is the location of the choroidal melanoma at the back of the eye. Protons, on the other hand, are lower in energy, and you can focus them in a way that they will peak in energy release right at the tumor. Terrific thing. This is called the Bragg peak. It's named after its discoverer in the 20th century. Now, the question is, how do you get a stream of protons? You just don't buy them anywhere. What they do is they take hydrogen atoms. This is a diagram of a hydrogen atom. Hydrogen atoms have typically one electron and one proton in its nucleus. And the protons and electrons can be separated in an electric field. You can envision a positive end of an electric field will attract the protons, the pluses, and a negative end will attract the electrons. Now we're dealing with atoms here, and you're really going to have a lot of a vacuum, nothing in between them. And typically what they do is when they separate them out from a hydrogen atom, they put them in an accelerator and keep them moving along so they don't want to come together. Okay? So the proton therapy apparatus is this huge, literally a building. It's essentially a cyclotron, and the water is separated here, and the protons go through this huge apparatus and through this gantry and this crane, etc., and they come to rest here, and here's the patient. These machines cost $100 million, but they're getting cheaper with time. There are a number of them in the world and also in the United States. So James was fitted with a mask to keep his head immobile, and he's fitted with a machine with a nozzle that would focus the protons right through the pupil of the eye, right to the back of the eye where the tumor was. The operation or the procedure was 2 minutes a day for 3 days. He was cured. The tumor was gone, preserved his eye, both structurally and functionally. Now, an issue arises with this therapy. It costs $100 million per machine. It's going to be a cost that has to be absorbed by someone. We want to know, is this, in a clinical trial, is this superior to other treatments? Well, the question of the clinical trial is going to be, what's the end point? What do we mean by superior? Does it mean more people who get proton therapy survive? That's one. Does it mean they have better vision? That's two, right? What about the cost-benefit analysis? How much does it cost to do this therapy versus the benefit in terms of survival? For choroidal melanoma, this has been an absolutely terrific treatment, this new radiation treatment. It's being used widely for some other tumors like prostate cancer. The data aren't in yet. It's not clear yet whether proton therapy for survival is better than conventional therapy. It's not worse, but whether it's worth the price to do proton therapy or not. This is a lecture in which I'm going to describe radiation therapy. First, we'll talk about, in some ways, reviewing how radioactivity damages cells, only this time specifically cancer cells. Previously, I talked about radioactivity causing mutations. Now we're going to cause mutations in cancer cells, hopefully kill them. Then we'll deal with the issue of overcoming the repair mechanisms that cells have when they are damaged by radioactivity. And finally, talk about how radioactivity is involved with stem cell transplantation for high doses of radiation and chemotherapy. So let's look at cancer cells and how they are damaged. Ionizing radiation is energy that's really strong. The photons that come out, the energy that comes out, is very, very strong. And what they can do when the photons come out is literally knock an electron out of its orbit. You remember the hydrogen atom I just showed you had an electron orbiting the nucleus. The energy coming out from a photon of a radioactive element is energetic enough to knock the electron out of its orbit. So here's a radioactive element. It's releasing both, as it decays, a particle and energy. And now we'll look and see what that energy does, especially we're interested in the energy here. Here's the photon. It can interact with an electron in another atom, and it can literally scatter that electron, and that electron is now energetic too. You're removing electrons from chemicals, making them highly reactive. It's a mess. The cell's going to get damaged terrifically by electrons traveling around with no place to go. They have to act, so they have to bind somewhere. And on the other hand, it will also release, some of the energy will get scattered as more photons. So it's a cumulative effect. It's like, it's dominoes, but it's a bunch of traps being sprung, and more traps and more traps. Each photon then causes another photon to be released, etc. So there's an extensive group of changes that are going to happen with radiation. Radiation damages not only DNA, but it damages the entire cell. And before I get to DNA, I'll tell you what happens in the rest of the cell. Radiation with these free electrons damages the membrane of the cell. You remember how important the membrane is to the integrity of the cell, and the membrane is involved with cell recognition and determining what gets in and out of the cell. Extensive damage to cell membranes by these free electrons. It damages proteins in the cell. The free electrons that are energetic will bind to proteins and completely changes their property. And you know that if you change the property of a protein, it'll change how its overall three-dimensional structure and its function. Some protons will some electrons, high-energy electrons, will split water in two and give more high-energy electrons. It's a mess, but we'll make the biggest mess with DNA. Here is radiation damaging DNA, hopefully, in our case, in a tumor cell. But let's look at some of the radiation damage of DNA. It will break these bonds called hydrogen bonds that hold the two strands together. Remember, DNA is a double-stranded helix, and the bases are on the inside. And I said they fit together. Well, they actually fit together by having a weak attraction to each other through something called a hydrogen bond. Radiation just breaks those bonds. And so DNA, which used to be all nicely curled, is now flopping around. DNA radiation will cause pyrimidine dimers, which are, remember, the two thymines that can bind to each other. Adjacent bases will bind to each other on the same strand. You know what that's going to do, because then when DNA replication tries to happen, it comes opposite two bases that are now askew, and so you can't make the proper bases. DNA will cross-link so it can't unwind. Proteins get cross-linked into DNA. Most notably, it causes double-strand breaks in DNA. Both strands are broken. I can't show that to you in any way. Bases will be removed. It's a mess. It's a mess, just with DNA. And you can imagine what it's doing elsewhere in the cell. So radiation is going to be a very good way of killing cells. And we want to kill tumor cells. How do we get radiation to a patient? Well, in the opening story, I described giving the radiation at a distance. In other words, remember he was fitted with a nozzle, and these protons came in through the nozzle. So the source was outside the body. This is called teletherapy. Teletherapy means radiation coming from outside. The photograph shows you more typical teletherapy. Radioactive cobalt releases radiation. The photons then come in, and typically there's a mapping going on. That is, the outside of the body is mapped such that a little target is drawn right above where the tumor is. For example, if it's in my abdomen here, the beam would be just zeroing in right at the spot where the tumor is below the surface here. And we shield the normal tissue against radiation damage, hopefully. Another way to do it is called brachytherapy. Brachy is a particle or leaflet. So this is brachytherapy. If you can see in the photograph, this is a actual X-ray photograph. These are little seeds. They're the size of a small grain of rice, but they're radioactive. And in this case, radioactive iodine, which is the typical seed, brachytherapy seed that's planted. A bunch of the seeds, a surgeon literally goes in and puts a bunch of the seeds, in this case, surrounding a prostate cancer. So it's right around the cancer. The radioactivity then releases, the radioactive element releases the photons and the energy and fries the tissue, we hope, and does all that DNA damage. And then the doc goes in and takes out the seeds again. Okay? Brachytherapy is notable also that it requires isolation of the patient, because the patient's walking around with something that's pretty radioactive, and so you don't want them to damage their loved ones who are visiting by the bedside. So they will stay in for a while. They'll stay in isolation for a while the brachytherapy is working. This can be a matter of days, typically. I want to tell you about the energy that's released, only because I want to just put things in perspective. The energy you absorbed in tissue per unit mass, okay? So energy per pound, right? Well, I'm going to give it in the standard way of doing it in science, joules per kilogram. Okay, that's like energy per pound, whatever. So 1 joule per kilogram used to be called rads, is 100 rads. The key in radiation treatment is how much are the target cells getting of this energy in terms of gray, right? 1 joule per kilogram. 1 gray in a cell will produce 100,000 ionizations, releases of electrons. It will also produce estimated 1,000 single-strand breaks of DNA, 40 double-strand breaks of DNA. 90% of the cells will die. That's 1 gray. Okay? Let's place this in perspective. Lifetime exposure of radioactivity for a typical person in our society, not a radioactive worker working in a nuclear power plant or whatever, but a typical, like I'm walking down the street typically, I'm exposed to some cosmic rays, I get medical radiation, etc., is 1/6 of a gray. So we're talking now about 1 gray and what it does. In radiation treatment, typically the whole treatment scheme is 60 gray. So that's way, right? We're talking about 1/6. It's 100 times the lifetime exposure, and you're getting it in a very short period of time. It's a whopping amount of radioactivity, and we'll see how we deal with that shortly. Radiation therapy has to overcome the tendency of cell to repair damage. I talked about BRCA1. That's a great molecule. It repairs DNA damage, just the kinds I've been talking about from radiation. So the challenge is, I want to kill the cells and overcome this, I want to overwhelm the BRCA1 or all these other repair mechanisms and kill the cells. I want to get enough damage that the cells will get killed, but I don't want to kill normal cells. Because if enough normal cells are killed, it's life-threatening. So we want radiation damage to be those DNA breaks, but we want it to accumulate in cells. Now, we're fortunate in dealing with cancer. That's not a nice way to put it, is it? But we're fortunate therapeutically in dealing with cancer in that cancer cells are dividing rapidly. And so DNA damage will get permanentized or fixed in those cancer cells, not repaired, but fixed before it has a chance to repair. Normal cells divide very slowly, and so they have a leisurely time to repair things. So the BRCA1 will come, it'll repair the DNA damage. Whereas the cancer cells are dividing quickly, they don't have enough time, and they'll go into programmed cell death if enough cells are damaged. So this is kind of the advantage for this therapy. It's targeted to rapidly dividing cells because they don't have a chance to repair. Let's look at how radiation kills cells. This is a graph showing on the y-axis is a logarithmic scale of cell kill. So the cell kill is on the y-axis, and as on the x-axis is the dose of radiation in gray. So we're looking at tumor cells and normal tissue cells, and we're seeing what kind of damage happens. And we're looking, and we're trying to estimate damage here. So let's say we want to kill 99.9% of the tumor cells. Okay, that's about, let's look at about 21 gray of radiation. Remember, 1/6 of a gray lifetime. We're giving a whopping dose, 21 gray. 99.9% of the tumor cells are killed. Unfortunately, over 90% of the normal cells are killed as well. If you look on the graph, you can see that. We got to do better than this, because there's too much collateral damage here, right? It's like the military. The military, you only want to fire on the target and not carpet bomb, right? You don't want to carpet bomb whole cities. There was so the idea is to give a smaller dose of radiation, and the smaller dose will be repaired in normal cells fully, but the tumor cell doesn't have a chance to repair it, so it'll be damaged. Then you give another smaller dose. And the normal cells repair it, they're back to normal. The tumor cell is damaged, so it'll get more damage. Then you give another dose. And the tumor cell will get a little more damage, and the normal cell repairs. You see what's happening? It's called dose fractionation. So we take this overall dose of 60 gray, and we divide it over typically 5 weeks. 5 weeks. And a patient will go in every day for 5 weeks, and they'll get a smaller dose of radioactivity. So the objective will be, let's damage the tumor cells a little bit. They'll repair a little bit, but the normal cells will repair completely. And we'll damage the tumor cells a little bit more, and they'll repair a little bit, but the normal cells will repair completely. So we keep doing that okay? When you think about damage, we can say we'll kill 99.999% of tumor cells. Wait a minute, a tumor this big, I'm putting up my hands here, this big, about a centimeter diameter, has 1 billion cells. So if you kill 99.999% of the cells, there's still 10,000 tumor cells left. A key to this radiation therapy, or any therapy, is what is called the therapeutic index. The therapeutic index is the key to any treatment in medicine. It relates damages to normal cell as compared to damage to the tumor cell in this case. The dream of oncology or any medicine is to have no normal tissue damage in targeted therapy, for example, and a tumor being completely damaged. Surgery, right? If you do surgery right and you take out the whole tumor and nothing else, that's great targeted therapy, right? That's perfect, no collateral damage. The word the surgeon will use, and surgeons are very unwise whenever they say this, is, we got it all, because sometimes they're proven wrong. Therapeutic index is very nicely shown in this series of diagrams. On the left, you have the favorable situation. On the y and the x-axis going up and down, it looks like it's damage, right? How much damage there is. And on the right is the dose. On the x-axis is the dose. And you see that for a tumor control, which is the solid curve, low dose can give a complete damage. 100% all tumor cells have been damaged. And at that low dose, in the perfect world, no normal tissue is being damaged. Isn't that wonderful? On the other hand, there's the unfavorable treatment, the one I just showed you, where if you're damaging 99.999% of the tumor cells, you're damaging 99.9% of the normal cells. Not a good idea. In addition to this therapeutic index challenge, we have the fact that some tissues are more sensitive to radiation than others. For example, leukemias, blood cancers are more sensitive. Breast is less sensitive. I wonder why. Breast has BRCA1, a terrific system at repairing radiation damage. Kidney is also not so sensitive to radiation damage. It repairs it, and so does pancreatic. So you will not choose to use radiation on treating pancreatic cancer. If we want to improve the therapeutic index, we can fractionate the dose, as I've just described. Fractionate the dose. Or we'll protect normal tissues by doing brachytherapy, for example, having these little seeds right around the tumor so they're not damaging normal tissue. We don't have a photon wave coming right through the body. No, we're just going to put it in right by the tumor. We can have chemicals that make tumor cells more sensitive to radiation. They're actually radiation sensitizers that tumor cells will take up only and make them more sensitive to widen the gap in our therapeutic index curve. A major challenge is the brain. There's a very narrow therapeutic index in the brain for radiation because those tissues are extremely sensitive. If I have a tumor inside my brain and a radiation beam comes through my skull, even if it's opened up to allow it to go through the tissue, there's going to be a lot of tissue damage, and you can't afford tissue damage in the brain. And surgery is very, very challenging in the brain also. That's why our characteristic of the smartest person in the people are always brain surgeons, right? So radiosurgery has been invented. Radiosurgery means that it's a common method. It's called the gamma knife. It's not a knife at all. It uses gamma rays, which are photons coming out of a radioactive element, from up to 200 sources. So there's small energy individually. You focus them all on a tumor at a specific spot. So here is a bunch of sources of radioactivity, and the gamma rays are all focused on this one target. That's what the gamma knife is. You can cut it down to a very, very small location, and it's a picture of a patient. So it's highly pointed right to the tumor, and it's got a pretty high success rate with little collateral damage. Overall, radiation is used sometimes as a primary treatment, where it can cure cancer in some cases. Usually, radiation is used after surgery, or along with chemotherapy as an adjuvant. Stem cell transplantation uses radiation treatment. And the story of stem cell transplantation is a fascinating one. It begins with the Cold War in the 1950s. The Cold War, for those who don't know, was a non-fighting war between Western democracies and Soviet communism. The fights would flare up periodically, but by and large it was cold. In other words, it wasn't hot. We had atomic bombs. We didn't want to do that to each other. But both sides were stockpiling ever larger atomic and hydrogen bombs. So the army and the government, of course, were concerned with what would happen if we were in a nuclear war. Well, radiation kills dividing cells. We found that out with the people in Hiroshima and Nagasaki. Their bone marrow was wiped out by radiation. Red blood cells, white blood cells wouldn't be produced. So the problem became, how do you protect people exposed to radiation in an atomic war situation? People did mouse experiments, and they found that if they had a mouse whose bone marrow had been wiped out by radioactivity, that is, the dividing cells were all dead, they could do a bone marrow transplant. You could take bone marrow from another mouse, and under suitable conditions, transplant it into the mouse that had lost the bone marrow because of radioactivity. And so they wanted to extend this to humans. The U.S. Atomic Energy Commission at that time, used to be now is the Department of Energy, gave a grant to a young doctor named Donald Thomas at Harvard University to try to do bone marrow rescue in humans. Now, there wasn't a war going on at the time. So instead, Thomas used people whose bone marrow had been wiped out by cancer treatment, radiation or chemotherapy. And so he began doing bone marrow transplantation. And the bone marrow has all of these stem cells. In 1957, he published a historic report on the first 6 patients. The procedure was safe. It was a phase 1 study. And bone marrow was then used on a number of more patients. And 20 years later, 1957 to 1977, they published a second study on 100 bone marrow transplants. Now, the idea here was, if we use high levels of treatment, radiation, or as you'll see later, chemotherapy drugs, that wipes out bone marrow, we could use a transplant to bring in the bone marrow cells. So I said it took 20 years for the first 100 patients. Now, today, 50,000 people are treated with bone marrow transplantation worldwide. The City of Hope Hospital, where I work, is one of the leading centers. They do over 500 procedures a year. Donald Thomas was awarded the Nobel Prize for this work. Now, an issue is radiation and chemotherapy harm the tumor, right? But they also harm normal tissues. So bone marrow is especially vulnerable, and the idea is to give massive doses of radiation, whole body radiation, to wipe out, if they wipe out bone marrow, it might wipe out the tumor well, and then you can replace with bone marrow that's stored from the self or other. Now, the tumors that can be treated with bone marrow transplantation, and this is no longer just bone marrow, range from blood cancers to neuroblastoma. It doesn't work that well on solid tumors for a number of reasons. Leukemias, lymphomas have been very successfully treated. We can now get stem cells for blood. There's some stem cells from the bone marrow that produce all these white and red blood cells that leak out into the general circulation, so we can get them there and purify them out of a patient as well. So you can just take it from blood or bone marrow. Either way, we can get those stem cells, store them in the refrigerator, if it's a patient, for example, and then treat the patient with a high dose of radiation or chemotherapy, then bring back and rescue the bone marrow. Now, the relationship between the donor and the recipient is a very important one. In the case of a person that I just described, called autologous self-donor, the patient's own bone marrow cells are removed, some of them, or stem cells from the blood, removed before therapy begins. That's called autologous. If a person has an identical twin, that's going to be really rare. The identical twin is genetically identical, so that's fine. It's called syngeneic. For many people, for many cancer patients whose bone marrow is not that healthy to start with, or they might have a cancer of the bone marrow, we use instead allogeneic, donor that's related to the person in some way genetically, but not necessarily personally with the recipient. The problem here is we all have flags on our cells that mark us for our individuality. So here's the flag. It's called the HLA system. And the HLA, the tissue typing is here. And here's the mother that has certain characteristics of her cell surfaces and the bone marrow. And she has 2 alleles, of course, M1 and M2, F1 and M2, F2. And these are very simplified view. and the children inherit various combinations of these. So these two children are a match because they have the same bone marrow. So this child could be a donor for that, for the sibling. Okay, so this could be a good allogeneic. What if you don't have a sibling? Then you have to go out into a registry and look for someone else who might be similar to you. In your HLA surface proteins, you have the same genetic constitution because there's a terrific number of alleles. There are thousands of alleles, different forms of genes for proteins on the cell surface, and everybody's kind of different than everyone else. So there are people out there who are just like you, but some of them are related, but some of them are not. So this is why you see drives for stem cell matching. So this is an advertisement showing father's eyes, grandfather's nose, father's smile, but none of their stem cells, right? There's no match available. And so we look in a database, and I've been tested, and I would urge you to as well. You just take a blood sample, and they can test your cells and find out what your genes are in case they need you. And this is a cartoon that it's kind of funny. They're using bone marrow from an animal, which actually doesn't happen. So it's a wonderful thing for everyone to do, and it's about a 1 in 100, typically about a 1 in 100,000 chance of finding a donor in a database who is distantly related to you. Where I work at the City of Hope, there's an annual donor-recipient picnic, and the recipient who got it and they saved their life using a bone marrow transplant, and the donor may be from far across the country and they've never met. It's a very, very wonderful thing to see, to save a life in a very simple way. So in this lecture, I've described treatment with radiation, how it works, the limitations of it, and stem cell transplantation that can help with it. If a tumor has spread to distant sites in the body, if it has metastases, we must use a systemic or blood-borne treatment, and that's drugs or chemotherapy, the subject of our next lecture. Thank you.